Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the cyclone separator. Let us first understand what a cyclone separator is and how it functions. Cyclone separator is a separation device which acts on the principle of inertia. Basically, it's a vessel with cylindrical top and conical bottom. Something like this. It has one inlet stream somewhere at the upper part of the cylindrical section and two exits, one at the bottom and one at the top. Typically, the gas containing some particulate material is fed into the cylindrical portion tangentially like this, and as it is fed into the cylindrical vessel, it creates a vortex, something like this. And usually the feed is fed with a high velocity. And the particulate matters, the heavier particulate matters rather, or larger particulate matters, they collide with the wall of this vessel and then they fall down and they are collected in this conical portion and they come out as a bottom product. While the lighter and finer particles, along with the gaseous portion of the feed, along with the vortex, they rise up like this and they come through this channel and exit this way. So this is how the gaseous portion and the solid portion, they are separated in a cyclone separator. There are various types of cyclone separator which we will discuss in few minutes from now. But in all of them, one thing is very common, that is efficiency. The efficiency means what is the extent of separation that we can achieve with that particular cyclone. The 100% separation is if the bottom product contains all the solids and the top product contains all the gaseous substance. But that generally doesn't happen. There will be a mixture of both of them. This will be majorly vapor and this side it will be majorly solid. But there will be some portion of solid at the top because of the finer particles, and there will be some portion of gas that will come through the bottom. Now we can perform some experiment with the cyclone separator and obtain the efficiency ourselves. For instance, if we have a XY curve, say this is the XY plot, this is the size, say in micron, and this is the efficiency, typically given by eta. Suppose the size range is from 0 to 50 micron and efficiency is from 0 to 100%. In Aspen, we write efficiency from 0 to 1, okay, in fraction. So if it is 0, it is 0. If it is 100%, it will be 1. Now, suppose this is 5 micron and we perform some experiment and we find that 50% of the particulate matter having the size 5 micron and above, they come through the bottom product. So we will plot somewhere here. So this is the 50% scale. Similarly, if we find through experiment that particulate matter having the size 10 micron and above, 70% of them, they come through the bottom product. Then we will plot 10 micron and 70% over here. Similarly, if we say that the particulate matter having size 15 micron and above, 85% of them, they come out through the bottom product. Then at 15 micron, we put another point over here. This is 85%. So we gather as many points as possible in this manner through our experiment, and we can get a curve of this nature. So this is the efficiency curve. Now, we will not get all the points. We can get this curve through interpolation, but this interpolation curve will give us some important information to us. So for any unknown particle range, say if we perform the same experiment with that particular cyclone, what will be the percentage of particulate matter having size 12 micron and above will go through the bottom product? If we have that kind of question in mind, then we know where it is. We'll put somewhere at 12 micron, and we can say that it will be somewhere 70, say 3% or so, based on the curve that we get. Okay, so this efficiency curve we should have in order to design or simulate a cyclone separator. Now let us go to the Aspen Plus simulation window and learn it better. So this is the Aspen Plus simulation window, and you will get the cyclone separator over here. In the model palette, you have to go to this solid separator, and here you will find the cyclone. So it models the gas solid separator using Cyclone. So you bring it over here. Here you will find the option of one feed, one outlet for gas, and one outlet for solid, as we have discussed a few minutes back. Now let us go to the block and see what are the inputs that we have to give. Now in model calculation option, you find that there are two ways that you can perform the calculation. One is solid separator and the second one is cyclone separator. In cyclone separator model, the calculations take place according to the theory of cyclone separator. And that theory includes the size of the cyclone, what will be its diameter, what will be its length, what will be the length of the cylindrical portion, what will be the length of the conical portion, what will be the angle of the conical portion, and so on. There are mechanical operation theories involved in it, such as settling, collision of particles, etc. Whereas in solid separator model, you do not have any such theory behind. It is just algebraic manipulation. You say that, well, in the solid separator model, I want my solid to be separated in this fraction. Then the Aspen Plus will calculate the fraction in that manner and give you the result. I will show you some example to learn it better. Now first let us discuss about the cyclone. Now here in the cyclone mode, you will find two options. One is simulation, another is design. In the simulation option, you give all the data. Like you give the diameter of cyclone, you give the data of length of the cylindrical portion, the conical portion, what is the flow rate. So all those necessary details you feed in, and you feed in the calculation method, that means the efficiency curve. So all this information that you have to provide, and it will simulate the model. Whereas the moment you choose design mode, you have to provide the design parameters. That means you have to provide what is the separation efficiency you have to achieve, and based on the desired separation efficiency, the size of the model will be determined. Okay, what should be the diameter of cyclone, what will be the length of cyclone, all those things will be designed based on the desired separation efficiency. So that is the design mode. So in both simulation and design mode, you have to provide the calculation method. Now in this calculation method, there are various models available which are there in the literature. Or you can use an user-specified model or user subroutine. In user-specified model, you have to provide an efficiency table. For instance, if you have a curve of the way that I have discussed a few minutes back, you will find the solid particle diameter and efficiency. So you have to provide this table. So if it is in micron, you have to say so for 5 micron, the efficiency is 50%. You have to write it in fraction. For 10 micron, the efficiency is 0.7, that is 70%. For 15 micron, the efficiency will be 0.85, and so on. And at 50 micron, in the example that we have discussed a few minutes back, for 50 micron, it should be 1. So if you provide this data based on your experimental work, then the Aspen Plus will do some interpolation. And this interpolation method may be any one of them. It may be linear, it may be spline linear, it may be spline RRSB or fitting. In fitting, these methods are known to you: Pleat method, Rogers method, Whiten method, Molera's method. You already know what they are. So you have to use any one of them for a good fitting, and you can use that particular separation efficiency correlation for your simulation or design, whatever. Similarly, the type of cyclone. Now, as I said that in the type of cyclone, what will be the length of the cyclone? Or what will be the diameter of the cyclone? Or what will be the angle of conical part? So all this information, either you can provide through your user-specified data, or you can use any one of these well-established type. And all those papers are available in the literature, so you can use them as you find it suitable. For instance, you use user-specified ratio. Then the ratio block will be open. And you will find over here length of cylinder on the basis of ratio of cyclone diameter. So this information, whatever has been asked over here, you have to give them as the ratio of this by cyclone diameter. Suppose this is the cyclone diameter. Okay. Then length, say this is L. You have to provide the data L by DC and write that data over here. So you do not have to give length of cylinder, rather you have to give L by DC. Okay. So height of inlet. Suppose this is a rectangular inlet that you are talking about. So the height will be A and width will be B. So you have to provide A by DC over here and B by DC over here. So like that you have to provide this information. Okay. And if you do not want that way, if you want to use standard types, then you can use any one of them. Now, to understand it better, let us go to the help file. It will explain in a better manner. So here you can see in the design mode how the cyclone diameter is calculated. Suppose you say that I want this much efficiency for my cyclone. Then how the diameter of the cyclone will be calculated? The diameter of the cyclone will be calculated using this particular formula, where Q will be the overflow gas flow rate, F will be the density of the flow, viscosity gas fluid, and rho is the density of the particles. Okay, so if you put all those data and solve for DC, now this is a nonlinear equation, okay? You cannot directly find it, so you have to do by optimization. So DC can be found out, the actual cyclone diameter can be found out based on this. Now let us go to the types and reference first. For instance, if we use the calculation method as Muschel-Knauss model. Okay, so what is Muschel-Knauss model? You can see over here, Muschel-Knauss calculation method. This is the Muschel-Knauss calculation model. So here we are not having any efficiency curve. So that efficiency curve we want Aspen to calculate based on some model called Muschel-Knauss calculation model. Based on this particular paper, you can, if you want, you can refer to this paper. This is the German paper that you have to refer if you understand German. Otherwise, the model has been given over here. Basically, the efficiency is given with this particular equation. This is the efficiency, where total efficiency is divided into two portions. One is strand efficiency and 1 minus strand efficiency into efficiency of vortex. Vortex, you know what just now we discussed. Vortex is, it creates a vortex when the gas comes with a high velocity. So the efficiency of vortex multiplied by 1 minus strand efficiency, that you add with strand efficiency. Now, what is strand efficiency and what is vortex efficiency? If you go here, you see this is the strand efficiency. Okay, it is 1 minus x max by x mean, and x max by x mean, what are they? This is the load. So solid load is given by x in, and maximum solid load, the loading limit, is x max. So x max by x in, 1 minus that will be the strand efficiency. And what is vortex efficiency? Vortex efficiency will be given by this particular equation. Now we have a factor of this nature. Now, if this factor is less than 1 by d, the vortex efficiency is 0. If it is greater than d, vortex efficiency is 1. And if this is within this limit, 1 by d to d, then we calculate it on the basis of this equation, where we find Wt vortex, and the Wt vortex is over here. And this vortex, this is based on V dot dch s, etc. Now, what is h? What is s? We do not know. These are all dimensions. Okay. To understand these dimensions, let us go to the cyclone dimensions. Here you find the dimensions are given. For instance, this is the diameter. All the cyclone model dimensions are given on the basis of the diameter. A few minutes back, we were talking about the ratio, right? So the length is given by L by dc, you remember? So the same thing will be given over here. So what is the length? Length of the column is h. So basically there you had to give h by dc. So this h is the length of the cyclone. Small h is the length of the cylindrical portion. A, this is the height of inlet channel. B is the width of inlet channel, because inlet can be rectangular, it can be round, it can be coil. Now for round, you can find over here, there is a round shaped channel. Okay. Whereas in rectangular, it is in rectangular shape. So based on what kind of inlet you have to provide appropriate data. And they are given over here. Okay. Now you see, inlet type, DC is the body diameter. A is inlet height, B is inlet width, D is the inlet diameter for round inlet. So for rectangular inlet, we have A and B. And for round inlet, we have BIN. And then height of overflow exit is called vortex finder, and diameter of overflow exit, cylinder height, overall height. So all these parameters are there. These are the terms, these are the description, and these are the types. Stram and HE, Stram and Barth 1, Barth 2, Barth 3, Barth 4, Lappel GP, Swift HE, Swift GP, etc. Now all those types are given over here. You can see. So all of them are here. Now these are all types of cyclone that you can use. For instance, if you choose Stearman HE, you see dimensions and ratios are not open now. Unlike here, the ratios were open, you had to give all those data because it is asking for user specified. You have opt for the user specified data. But the moment you use, say, Stram and HE, then this is off. This is no longer available for you, because the moment you use Stram and HE, then all those ratios are given over here. You see, say Stram and HE, body diameter ratio is 1. Obviously, because everything is compared with the body diameter. L by D or H by DC. Okay, it is given by DC, right? Yeah, it is given by DC. So L by DC, H by DC. So DC by DC is 1. A by DC is 0.5. A by DC is 0.5 means the inlet height of the channel is half of the body diameter. So if you compare in this diagram, you can see this is A and this is DC. So what it says that A by DC is equal to 0.5. That's what it means. Similarly, all other ratios are given. So the moment you choose TREM and HE, all those ratios are automatically taken by Aspen Plus. If you choose something else, birth 1, birth 2, etc., then accordingly the ratios are taken and you do not have to provide any value separately. Right? Similarly, you go to calculation method, which is Lathe-Lech model. So this is Lathe-Lech model. This is given by this particular equation where eta is equal to 1 minus exponential of this term. Here you will find three unknowns, C, phi, the capital phi, and n, where n is a function of d and t. D is the outlet diameter. Outlet diameter means this is the outlet diameter. And T is the temperature in Kelvin. So if you provide this information, N will be calculated. Phi is the combined effect of particle and gas properties. You will find the particle density, particle diameter, viscosity, Vi is the gas velocity. Okay. And N you find from here. So phi is calculated. And C, the C is the combined effect of geometry properties. So all the geometric property, A, B, diameter of body, height, all those things are combined over here through this equation, and you can find C. Okay, so that's how you choose the type and the dimension or the calculation model. Similarly, you can use Shefford and Lappel model, modified Lathe-Lech model, Dietz model, Motz and Lofer model. Now you can go and find what these models are from the help file, or the references are given over there. You can go to the reference directly and find out yourself. Okay. Now let us solve some example to understand it better.